Please welcome Emily.
Thank you. Cheers. All right, so who wants to improve their training performance? Okay, everybody, right? Yeah, move it from days or weeks down to hours or minutes. And so today I'm going to talk about training performance. There's a lot you can do in your scripts, maybe make your models train to a certain accuracy faster. But I'm going to leave that for y'all to experiment based on the great lessons from other speakers today. And I'm going to talk about training performance specifically coming from your testbed configuration, both hardware and software. Things that are a little bit more ancillary sometimes to that core data science, but are equally as important for overall throughput of your training jobs. All right, so this is the conclusion slide. So in my testbed, I saw between two checkpoints in time, 9 months apart, a 2.5x performance increase. So my throughput of images per second increased by 2.5x. So what changed between those two checkpoints? I'm using the exact same hardware, the same compute and GPUs. The whole setup is the same. I have my same script that I didn't change. But I did take new versions of the software stack, of the hardware drivers. And with that new software stack, you do get some new tunables and ways that you would kick off your script. But it really is the same script, exactly the same, and the same hardware underneath it. So you can think of it a little bit like you built your car, you're still driving the same car, but it's on a much better road now. So let's talk about some of the lessons that I learned through this experience. Number one, know where your bottleneck is. So a deep learning training job is a pipeline of tasks. And any pipeline should be balanced to be efficient, or else you have one piece of it that's the bottleneck, right? And a lot of times for deep learning training jobs, our first thought is to go say, let's look at the GPUs. Are the GPUs bottlenecked? That could be it, but it also could be work that happens across GPUs. It could be part of the networking. It could even be in loading your data sets from where they're stored into the GPU training jobs. So this is what my test bed looks like. We're going to use it as an example today. It has a couple of really beefy GPU nodes, 4 of them, each with 8 GPUs. But I work with a lot of kind of enterprise-sized companies, but this same principle of the impact of the software stack also holds true if it's condensed down inside of a single laptop. All right, so where's the bottleneck? Okay, if you've used NVIDIA GPUs, you know there's a cool tool called NVIDIA SMI, and you use it to check GPU utilization. And it's great, but it's not totally comprehensive of what's going on, and it's not super granular. I can look and say, wow, in micro print you probably can't read, it says, oh, everything is above 90% utilized in the GPUs. But how do we look elsewhere? We really need to take the entire pipeline, and we need to break it into pieces and test the pieces individually so we know which of them are not performing up to their potential. So what we did on my team is we said, how do we know what good is? Well, let's say linear performance is you take one GPU, have its throughput, let's just multiply that by 32, and you should be able to get 7,200 images per second. Well, when we ran a job in practice with 32 GPUs, we got about 4,000 images per second. That's a significant gap. The defaults just means we're going to use the same hardware throughout, but we're going to be doing some tuning here. So with the default, we had a 42% performance gap. Where is the bottleneck? So one thing we did was we ran with synthetic data instead for some jobs. So synthetic data is generated on the GPU. It doesn't look like real data. And most importantly, you're not utilizing the path of pre-processing your data from your storage through your CPU. It really highlights the GPU side of the work. Our synthetic performance was actually quite close to linear. So that means that most of our bottleneck seems to be in the work that's happening before the GPUs are doing their work. So just for a quick refresher, let's take a look at what some of that work is. This is the joke. I have to tell people it's a joke because I've tried it a lot of times and it's not obvious that it's a joke, sorry. But in papers, a lot of times, an input pipeline looks like this, like image on a stick. And in reality, there's a lot more actions going on under the hood there. The input pipeline of loading that image into the model looks like listing out all of the files in your data set that are participating, shuffling them, doing the transformations and distortions on your data, and copying to the GPU for every batch. So this is a complex set of work that exists when you're reading from a real training data set and not when you're doing that synthetic test. But now that we know where our bottleneck is, we're able to look and tune specific parameters that do impact that set of work. So for example, we were able to get some performance gain by changing this prefetch queue length. We were able to get some more performance by changing some thread pool rules specific to input pipeline. And then the last thing we did to get close to our synthetic performance was disabling distortions. So that's kind of, we felt kind of uneasy about that because in reality, we do want to be training with distortions. They're pretty useful. So now that we had achieved that near synthetic, that takes us to our next point, which is consume new software. Because distortions gave us a performance improvement. When we ran without distortions, we were faster. But look, with new software, it's pretty much equivalent when you're running with or without distortions. So the two bars on the left are from that original checkpoint 9 months ago, where you can see that running with distortion, the orange bar on the right, you do have lower throughput on your system. And now, thanks to great development from the TensorFlow team, from the community, we're now seeing, with no change on my part, I didn't do this work, I just got this for free, now I can run with distortions and have equivalent performance. Another nice thing about knowing where your bottleneck is that you can be on the lookout for specific software improvements that might be interesting for you. For example, I might see that a specific code release has something juicy that impacts my bottleneck area, and I should take it. And when you're on the lookout for these, then you can tune and take best advantage of those new changes. So while the input pipeline performance by default has improved a lot over the past year, there also have been added some new tunables that impact this input pipeline, but I have to know about them to take advantage of them and to tune them for my system. So the TensorFlow team, and I know other libraries, are working really hard to do some auto-tuning and to help get that out of the user's responsibility. But the truth is that today, there are definitely performance gains to be had by knowing which tunables to set. So this is just to demonstrate the gray bars on the left are without this new tunable that was recently released that impacts input pipelines, and you tune that and get even further gains. All right, let's talk about lesson 3, asking more from your libraries over time. So things that didn't used to be possible might be possible today. You should try them again. I'll give you an example. OK, let's have a refresh of the life cycle of a batch. So you break your data into a subset of data, a batch, and it's going to get fed through the CPU for preprocessing. It'll go through GPU or TPU for compute. And how you break apart your data into batches affects how fast you can complete your overall work, right? So to show that, I have, on the left, gray bars, you have a small batch size of 64. I guess it's not that small. We definitely have all worked with, seen batch sizes of 3 or 4. But it's lower than the orange on the right, which is 256. So 256 batch size gives me higher throughput, which means I could finish my job faster. Why wouldn't I want to always do that, right? Well, you might run out of memory. Has anyone had an before? You should. You should try to hit it. Try to hit it. And ask for more from your system. Because while we used to hit this now I'm able to produce that graph for you because the system now is able to do memory management that better supports those bigger batch sizes. Again, just by taking that new software, that higher throughput of a larger batch size was enabled. All right, lesson 4. This one is really easy. Has anyone heard of FP16? OK, nobody. Nobody raised their hands. So we need to go back to some other presenters that mentioned it earlier. So FP16 uses lower precision, lower data is going through the pipeline, you can get through with it faster. It is a possible way to improve your training performance. So major changes like this in the industry are something that you can try. A lot of workloads are ripe for switching from FP32 to FP16, especially appropriate if your sensor data is already low precision in the first place. All right, the final lesson real quick is to consider the whole stack. So a lot of times you'll see people talking about the upper layers. So the Docker container, your libraries, your CUDA, whatever you have as the GPU software. It also includes the hardware. Like in my system, I have GPU hardware, I have networking software, networking firmware and hardware, and I have storage firmware and hardware. And each of those not only depends what they are, but how they're tuned as well. You're not supposed to be able to read this, but it's to show you that every setting for every component in the system can affect performance, and I need to at least be aware of what all of those settings are set to right now. Real quick story to demonstrate that. Silly mistake, when I inherited my test bed a long time ago, I thought that it looked like this. Secretly, it looks like this. So if you're a data scientist like me, you might think, a management network, why does it have extra switches? But it does. It has beefy switches. The two in the middle are for the data path, and it has a management network to manage the system that's also there. Well, when you accidentally run your training job over the management network, you're going to be using the 1 gig Ethernet instead of the 100 gig. So your training performance will be 1/100th of what it should look like. And hopefully you don't make such a silly mistake as that. Just trying to show you that the whole system can impact everything altogether. All right, so in conclusion, when is the last time that you guys pulled a new version of software? Okay, well hopefully this will remind you to try updating things, to try refreshing things, to try more and update the parameters of your jobs. The folks from the development teams and the community are doing a great job pushing the performance inherent to those libraries up higher and higher. So things like the cloud repo to take a whole software stack at once can be a great way to take advantage of those completely brainlessly. All right, so I wish you guys luck on your developments and on increasing your own training throughput. Thank you.